Section 8-1, direct variation and proportion. Our main objective here is to define direct variation and solve problems involving direct variation. First, we'll start and take a look at the equation y equals kx, where k is considered to be what's called the constant of variation. And what direct variation really means is simply that as x increases, y increases. So as this quantity x goes up, this quantity goes up. And let's take a look at that. Pick a random arbitrary value for k, some constant, like 2. Our equation becomes y equals 2x. And if x is, say, 3, we get y equals 2 times 3, or simply y equals 6. But instead of x being 3, let's say that x becomes 12. Then as a result, we get y equals 2 times 12, which really makes it y equals 24. So what we'll notice is that as x increases by a given factor, right, a factor of 4 here, the y value also increases by a factor of 4. The last thing to look at is to note is that k we call the constant of variation, but really it's just a slope. It's a slope, just like our slope in y equals mx plus b form. This is our slope value here, a slope of 2. Example 1 says y varies directly with x. When the value of x is 4, the value of y is 24. First find the constant of proportionality, that same thing as the constant of variation. Proportionality is the same thing. And then find the value of x if y is 18. So we start right away by saying y equals kx because we know these are directly related. Y varies directly with x. That's the equation we write every time. Then we go ahead and plug in what we know. We know that x is 4, and we're told that y is 24. So what we're missing here is what goes here. That's the k value. So it says find the constant of proportionality. That's what we're looking for, k. So k turns out to be 6. You can get that by dividing by 4. So when k is 6, we could rewrite the original equation here, which we'll call the generic equation, with a specific equation, y equals 6x. 6 specifying that we have a slope of 6, or a constant of proportionality of 6 in this problem. And then the problem says to find the value of x when y is 18. So when y is 18, we put 18 in there, and we're trying to find x. So solve for x by dividing by 6, and x is going to give us 3 in this case. So this was our first answer, a constant of proportionality of 6, and then when y is 18, x turns out to be 3. Now in this example here, we can note that we're using variables y and x, and you might say, well, what does that even mean to us? But we have to think about the fact that there are a lot of things that do vary directly. So we're generally looking at the idea mathematically, but application-wise, we can think of so many things. I mean, think of like something like a spring. The more force that's attached to the spring, the more the spring stretches. Or, for example, there's a general direct variation between height and weight. As somebody gets taller, they gain more weight. Now they could get taller and skinnier, obviously, so there's exceptions. But generally, if somebody was continuing to grow at the same proportion and they just getting taller, they would be gaining weight as well there. Now this next example makes total sense, especially if we think about real-life applications. We see that the paycheck for a salesman, P, paycheck, varies directly with the number of hours worked, W. So paycheck is the amount of money they get paid, so like $80, varies with the amount of hours, say 5 hours, whatever. So it says when the salesman works for 12 hours, his paycheck is $96. What is his paycheck when he works for 17 hours? So we could set up a fraction and look at it that way with a proportion, but we could also use a direct variation equation. And the reason we're going to do that here is to see what it actually means. So we'll start with P equals KW. Right? The paycheck varies directly, that's the K, with the hours worked, W. So we're told that when the paycheck is $96, we have here K times a value of, 12 hours. So K turns out to be 8. Now you might ask yourself, what is the significance of that 8? Well, this is where units come into play. If the paycheck is $96 and there have been 12 hours of work, then you're dividing dollars by hours to get the K by itself. So it's $8 per hour. This is how we can think about units and dimensions and how they help us understand what a problem actually means. So again, how would you solve for K? You would divide by the 12, but so you're dividing by hours. You have dollars, so this is going to be dollars per hour. So K is really the person's hourly rate. This is the person's hourly rate. Although it's not asked for anywhere in the problem, we need to know what the hourly rate is, because now we know he's worked 17 hours. So this is easy now. We could say here's the specific equation, 8W. Again, here's the hourly rate. Here's the amount of hours worked. So 8 times 17. We're going to just plug in the 17. And we'll see if we look at our units, right? Dollars per hour times the amount of 17 hours. Right away we see cancel, cancel. 8 times 17 simply gives us 136. Well, what are the units of this? The units are dollars, because we're left with dollars here, and that makes sense, because his paycheck needs to be in dollars. It's also important to note that you could have solved this equation by saying W equals KP, but then the units would have been a little bit odd. You would have got a value of K of 1/8, and it would have been hours per dollar, which means it would be like 1/8 of an hour every dollar, which is exactly what's happening here, but it'd be like the inverse of the situation. You'd still get the same answer in the end, but the units would look weird. So I would put it in this direction because it makes sense when you divide now. This is your hourly rate. Alright, example 3, back to variables, just so we can see a different type of proportionality. If A is directly proportional to the cube of B, or B cubed, and A is 10 when B is 2, find A when B is 4. So A is directly proportional to B cubed. Now we're told when A is 10, B is 2. So this is really going to be 10 equals K times 8, or simply K equals 10/8. Now, if K is equal to 10/8, we reduce that, that's 5/4. Okay, so we have A equals 5/4 times B cubed. Again, this was my general equation. This is my specific equation, specific to this scenario. Now we're told when B is 4, find out what A is. So when B is 4, find out what A is. So we could simplify, right? 4 cubed is really 4, 4, 4, and there's a 4 in the denominator. So I could go like this, cancel, and make this 4 squared instead. Because this is really, again, 4, 4, 4, and this bottom here is a 4. So it really becomes 5 times 4 squared. So 4 squared comes first, obviously, PEMDAS. So 5 times 16, or simply 80. And notice right now, and it's a little bit interesting to see, a small value of B of 4 produces a large value of A for 80 because it's directly related to the cube of B. So even though the small number here is a 2, A is a 10. Well, this is only doubled, right? It went from 2 to 4. It doubled in that sense. But this went from 10 all the way up to 80. An increase by a factor of 8. Because again, we're looking at cubes here, cubes. If this doubles, what's the cube of doubling? The cube of doubling is a factor of 8, and this goes from 10 to 80. So the period of a pendulum, well, let's think about first of all what is a pendulum. Here's a pendulum. Okay, it's a bob. This is called the bob. Bob just means the object at the end. The period of a pendulum, the time it takes to do this, and come back. So to go from the start to the other maximum displacement over here, and then return to its origin. That's the period of a pendulum. We're told that the period is directly related or directly proportional to the square root of the length. That's what I would write. So again, the period is directly proportional to the square root of the length. Now we know that if a pendulum is 64 centimeters long, has a period of 1.6 seconds, figure out what the period is of a 100 centimeter long pendulum. So let's find out what K is first. So square root of 64 is 8. Now I'm dividing 1.6 by 8. It's like 16 divided by 8. That would be 2, but since it's 1.6, this will give us 0.2 for K. So our specific equation becomes, and then all we have to do is go ahead and say, oh, if the pendulum is 100 centimeters long, we can find the period. So the length of the pendulum is 100 centimeters. Find the period P. So the period turns out to be, the square root of 100 is 10, and 10 times 0.2 is just going to give us 2. And what are the units here? Well, the units were seconds, and these units are seconds. How do we know that this makes sense? Well, we could see here that a short pendulum of 64 has a period of 1.6, while a longer pendulum will have a longer period.